Hello and good evening. I was just waiting for you guys to show up in the meeting, but it seems like no one is online so far. So I'm going to just start and make the recording for the next 30 minutes, and then I'll put it online for you to watch later at your leisure. What I'll do is I'm going to review three problems related to fatigue failure, and they show basically how to design a component against failure due to yield by plasticity or due to fatigue with a limited lifetime or for infinite lifetime. Also, the problems are going to discuss how we can combine different types of stresses using von Mises criteria. So if you look at problem number 22 in here, number 20. So problem number 20 is a bar of steel. It has minimum properties of S endurance, 40 KSI. The yield is 60, and the ultimate is 80, and is subjected to a steady means constant torsional stress of 15 KSI and an alternating bending stress of 25 KSI. So you note here that the loading has two different types of stress. One torsional, which is pure shear, and the other one is alternating, which is tensile or compressive. And then the question is, we wanted to find the factor of safety against static failure, meaning that we wanted to make sure that on the first cycle, we don't have failure by yielding. And then if the component survives the first cycle, then we want to find the factor of safety for fatigue failure using different criteria. So I'm going just to focus on the first one, modified Goodman, and the other ones I'm going to quickly refer to how to do the problem. So in this problem, if I look at it, then what I need to do is I would like to find the equivalent stress to the 15 KSI torsion and the 25 KSI bending. And to find this equivalent stress, I gotta use, the easiest way is to use the distortion energy criterion and use von Mises. So von Mises, if it is simple like that, then the equivalent stress would be the square root of the bending stress square plus 3 times the shear stress square. So if you look at the solution, then the first step is to find the equivalent, to write it down so that I have the mean stress is 15 and shear is 15. The alternating is 25 bending, but sigma mean is equal to tau alternate is equal to 0. So we combine tau mean with sigma mean with the usual von Mises equation. So we can get sigma alternating equivalent. And it turns out to be, when you go 25 squared plus 3 times 0 squared to the 1/2, you get 25. And we do the same thing for the mean stress equivalent. So the equivalent means you just combine all of the mean values of the corresponding stress tensor, all of the components, you put them into the von Mises in that fashion. Since we want to guard against yield, so we want to make sure on the first cycle, the maximum stress does not exceed the yield. So if I add up the mean plus the alternating of the von Mises kind, then I should get the maximum, and the maximum should not exceed the yield. So I should get, first I gotta find sigma max, and sigma max is sigma alternating plus sigma mean. So sigma alternating is 25, and sigma mean is 0. So this will give me a 25 squared plus 3 times the alternating plus the mean of the shear kind squared. So it gives me 36. And then I gauge that against the yield strength of the material, which is 60. So the factor of safety is the maximum allowable, which is 60, divided by the actual stress for the first cycle, which is 36. So we get a factor of safety of about 1.7. Now we go further to analyze the situation when we have fatigue. And fatigue, now we just combine the stresses, and we forget about the original set of stress values, and we just focus on the von Mises values. Now, because we have the alternating, we have the mean, we have, when we can combine them together and use modified Goodman. And modified Goodman, as we know, it is the alternating divided by the endurance plus the mean divided by the ultimate, and that should be equal to 1 over n. So if you solve for n, you will get 1.05 from this solution. So this is the alternating divided by the endurance. The endurance for this problem is given to us at 40. I guess the problem here has 40 already, so we know that the endurance limit is 40, and then the ultimate is 80. Note that because it's a steel, ductile steel, then the endurance limit is half of the ultimate strength of the material, as we learned in class. The other criteria are similar. The only thing is that if you do for Gerber, for example, then Gerber has a parabolic term. Remember, in Gerber, we have 2 terms. One that has the mean divided by the ultimate but squared with the n in it, and the other one had the alternating divided by the endurance limit. So when you factor out the n, you have like a quadratic equation to solve for n. In the book, the solution is already given in table 6.7, but on the test or by yourself, you can just rewrite the solution and solve a quadratic equation very easily, and solve it for the factor of safety for fatigue. And here it turns out to be 1.31, which means that Gerber give us a little bit more margin than the modified Goodman. As we know that the Gerber has a little curve, so it just gives you a little bit more margin than the modified Goodman, because a Goodman is kind of a straight line. So that's for the problem 620. And now I'm going to review 2 other related problems. And the idea for the 2 related problems is to kind of go into a progression of steps. First, we test against, here we tested against yield and then infinite life. But it's possible that we have loading. The loading, we don't know the results, so we have to test against yield. We have to test against infinite life. And if it doesn't work either way, then we have to test against finite life and find the number of cycles to failure. So that's kind of the 2 related problems that we have here. And this problem is 625 and 626 and 627, very related. So let's read the 625. We have cold drawn IC1040 steel, and which is, you can see here. So it has a hole in the middle, and it has 25 millimeter width, and the hole is 6. So the hole is kind of taking away some of the load carrying capability of that component because the area has been reduced. And it's fully reversed between 28 kilonewton in compression to plus 28 kilonewton in tension. And in this problem, we want to estimate the fatigue factor of safety based on achieving infinite life. So for this problem. And then we also do the yielding factor of safety. So it's similar to the earlier one, except here that we have to make sure that we account for the fact that the load carrying capacity of the component is reduced when we calculate the stress on the section. Also, because it has a hole, as we learned, we have a stress concentration factor, and that stress concentration factor has to also be applied. So in problem 626, we repeat this one, but the load is fluctuating instead of from 28 to minus 28 to plus 28. It is fluctuating from minus 12, from 12, positive 12 to positive 28. So let's take 626 and use the modified Goodman, and of course we can apply the other criteria as well. So if we go like here, 626, the first step is we have to check for yield. And we gotta find the properties of the alloy. So we have the alloy is 1040 steel, and we have a table of properties at the back end of the book. It gives us the ultimate 590 and the yield 490. And from those, we also have the endurance limit is 208.6. So this is from the properties of that material, IC1040. So we got the material properties. The ultimate, of course, is important. Yield strength is important because we have to guard against yield. And then the endurance limit is going to help us determine whether we have an infinite life or a finite life. So we look here, we see that the maximum force is 28, the minimum is 12. And we know now that we need to calculate the stress as the force divided by the reduced area. The reduced area is the thickness times the width minus the size of the circular hole. So it's 25 minus 6. And we get it in Newton per millimeter square. And that's exactly the same as in megapascal, because 1 meter is 100 millimeters. So when you square it, you get the factor of 10 to the 1 meter has 1,000 millimeters. So when you square it, you get 1,000,000. So 1 Newton per millimeter square is the same as megapascal. So it's something quick that one can use in quick calculations. So once we figure that out, this is the maximum, then we find the factor of safety against yield by saying that the maximum allowable is the yield strength, and the actual stress is sigma max. And when we do this calculation, we get 3.32. So it is safe against yielding for sure on the first cycle. Now we go to determine the fatigue factor of safety for infinite life. We tested to see infinite life. Endurance limit is 208. The stress concentration factor is 2.2. We have graphs in the book that shows the stress concentration factors for tension compression. You have a hole in a plate, and we find the value to be 2.2 based on R over D and D over H values from that relationship on the graph. So we get 2.2. And therefore, the alternating stress will be maximum minus minimum divided by twice the area times the stress concentration factor. And then the mean is the maximum plus the minimum over twice the area times the stress concentration factor. Note the area is reduced in both cases here. And now we are ready to assess infinite life. And in this case, we would have, if we use modified Goodman, it is 1 over n. You have the damage due to the alternating stress, it's ratio to the endurance limit, and the damage due to the mean, which is ratio to the ultimate. It should give us equal 1 over n, and we solve for n and get 1.2. So similar to the previous problem. And in fact, if we do the Gerber, we get a solution for the quadratic, and we get n equals 1.49. Now, if we just go back and repeat the same problem, which is in 627, but we take the load to vary from 0 up to 28 kilonewton instead of from 12 to 28, we go from 0 to 28, same thing. So let's see what happens in this case. So what we see is that in this case, we're using the same material properties, and the forces, the minimum is 0 and the maximum is 28. So we can get the maximum stress, this is the force divided by the area, still the same, but and we haven't really changed anything as far as the yield is concerned, so we're okay. But now we're going to try to check for the infinite fatigue life. When we do the calculation for the infinite fatigue life, we have sigma alternating. We will find that because the minimum is reduced now from 16 down to 0, that gives you a wider span. And when you do the calculation, the alternating stress becomes 162.1, and the mean stress also becomes 162.1. And when we use the same properties of the material, we find that the factor of safety against infinite life for fatigue is less than 1. It's 0.95. So in this case, we discovered that the component is not going to last forever and is going to last for only a finite number of cycles. So that takes us back, and we have to use the SN curve. So remember the equation defining the relationship between S and N in the zone 2. Like, remember, we had 3 regions, low cycle fatigue, and then high cycle fatigue, and then we had infinite life. It turned out to be potentially in the high cycle fatigue because N was very close to unity. For infinite life, it means that the number of cycles will have to be quite large, maybe 10,000 or 100,000, and therefore we would just get a guess that it is in the high cycle fatigue region. So first step is, because we have a component that's alternating of the stress, another component is mean in the mean value. We cannot directly use the SN curve. We have to make an equivalence for a fully reversed stress, as we discussed in class, using any one of these failure criteria. If we choose the modified Goodman, then the fully reversed is the sigma alternating divided by 1 minus sigma mean over sigma ultimate. And when we do this calculation, we find that the alternating actually, it used to be 162.1, but when we combine that, when we combine the damage due to the mean, the equivalent fully reversed becomes 223.5. So it's kind of larger. And therefore, we can use it now in determining the lifetime. So now we go to the story. We'll switch to finding the equation of the straight line on a log-log plot. First, we're going to find the factor F that determines the fatigue life at 1,000 cycles, because that's kind of the lower bound. And we know the upper bound is the endurance limit, or the endurance strength at a million cycle. So between these 2 points, we are able to find the constants A and B in the power law. So from the figure 618, we find that the fraction of the ultimate is 0.87. This is the fraction of the ultimate that gives us the fatigue strength at 1,000 cycle. So it's 87% of the ultimate strength of the material is the value of the fatigue life, fatigue strength at 1,000 cycles. Once we find F, then we find the two constants, A, which is Fs ultimate square over Se, is 1263, and we find B, and we said in class that is negative, so minus 1/3 log Fs ultimate over Se, and when we do that, it is minus 0.1304. And then after that, we solve the problem for sigma fully, we know sigma fully reversed, which is 223.5. And we know that the Sn relationship is, this is S, which is sigma fully reversed, is equal to A times B to the power B. So when we solve for B, we solve backwards. We just put everything on the right side, and then we find that N is actually quite large. It's 586,000 cycles, as we were just guessing it before we solved the problem. So I think with this, we have a series of problems that show us how we can apply the factors of safety against yield, static yield, against fatigue, high cycle fatigue, and also checking to see if we have infinite life. So with that, I think we're going to stop here, and I'm going to post it on our website. See you in class.